So now we're into chapter 3, and we're looking at different boundary conditions. And in this video, we'll just look at the case of an insulated rod. That's our key thing anyway. And then we have some A temperature down here and some B temperature here. And so this is all insulated. There's my insulation. Maybe it's fur. I don't know. And so we'll have with this. So we have our U sub t equals alpha squared U sub xx and some U0 of x is some g of x. Now, so if we first look at A and B constant. Okay, and we've already looked at that in earlier chapters. So A and B are constant, so A equals some A0, B equals some B0. Then what we know is, we expect something like let's just go down here. So here's 0, and we'll say a length L, and so this is the x-axis, and then we have U here, and suppose we'll let A be less than B. We'll put A0 at that height, and we'll put B0 at this height. Then, who knows exactly what U0 of x is, but, so suppose we just say, oh, I don't know, it's something like this. So here's t equals 0. But then with these, if I put a point there and then out here at L for B0, then what we expect over time is to head toward that line. So again, this is U at infinity, t equal infinity, and x, so oops, t equal infinity, and so this is U of 0 and x down here. And so, this, and actually because the boundary is held at that temperature, this should very quickly up here, drop down to here, and this should very quickly go to here, but the stuff in between will take longer, and it may do something, and I'm going to draw it so it goes right through there, although I'm not sure it would have to. But so this is t equal t something, t1 or something, we'll just call it, and and this will be heading toward that line. So that would be constant boundary conditions. Now though, suppose they're not constant. Suppose A is A of t, and b is b of t. You know, what the heck happens then? Well, the thing is at any given time, right, if I were to try to draw this thing again, you know, here's 0, here's L, this is X, this is the U-axis. The problem is, you know, if those are functions, then at any given time, you know, it could be, say, you know, here's a 0 and B0, we'll say, you know, and so initially at some given time, we would be trying to get to, now this isn't what the temperature would look like necessarily, but we'd be trying to get to that line, and so, you know, maybe this is t equals 0. But then, who knows, you know, maybe at some other time A1, t equal 1, whatever the time units are and so forth, and maybe this is B1, then we'd actually now be trying to head to that line. Okay, so who knows what the heck is happening in between all that, right? You know, if the time units are sort of slow enough, then certainly, you know, we would expect not long after t equals 0, so I'll put t equal 1 here, not long after t equals 0, depending on what the initial conditions would be, you know, we may see something, you know, who knows, kind of like that, where it's trying to get there. But then imagine, you know, at T1, not too long after that, well, all of a sudden, you know, so then, well, we're probably, you know, we've brought the boundary condition here and the boundary condition here. And so, you know, it might all of a sudden here look like, since that was lower down here and higher up there, it might, again, I don't know really for sure what would happen, but, you know, it might be, you know, doing something, let's see, where are we? Yeah. You know, doing something more like that at that point, you know, so, you know, we would have something like that maybe. So here's u of 0 and x. Here's maybe u of 1 and x. And depending on how those boundary conditions change, you know, this thing could be moving all over the place, and we wouldn't have that steady state situation where, you know, it ends up heading to a line unless the boundary conditions ended up heading to a constant. Okay, so if the boundary conditions were such that they were changing to a constant, then, you know, then we would have a line at some point. But, you know, but unless that happens, now, you know, this thing would just, you know, it would be all over the place, here at some point, you know, here at some point, and something else at another point. Okay, so we really couldn't say what it looks like at all, other than, you know, it should, because of the boundary changing and forcing it to kind of head to that condition right away, right at the boundary, you know, we'd probably see things like I drew here, you know, where it looked, you know, where it was attaching to whatever the boundary value was at that point, but who knows what goes on in the middle. Okay. And then just to enlighten you a little more with their two-dimensional case here and the polar coordinates. So, you know, they have this circle, and, you know, here's theta equals 0, theta equal pi over 2, theta equal pi, theta equal 3 pi over 2. And, you know, they're saying, hey, in this case, the boundary condition is that, you know, and they have u of uppercase R. That's how we know it's the boundary, because they're saying this radius is uppercase R. And then theta and t. So the boundary condition changes not just with time. So here's the time part, cosine t, but also with theta. And so if we want to look at, you know, t equals 0, in that case, cosine of t is equal to 1. And I'll just fill this thing in for sine. And here we would have sine of 0 equals 0. Up here, we would have sine of pi over 2, which equals 1. Down here, sine of 3 pi over 2, which equals negative 1. We get 0 over here. And, you know, if we did like 30 degrees, 60 degrees, then I know that's a half. That's square root of 3 over 2. That's square root of 3 over 2. That's a half. Negative a half. Negative square root of 3 over 2. Negative square root of 3 over 2 and a half. And I could have my square root of 2 over 2 at 45 degrees in there. But so what happens, that's just the normal sine curve. And so if we were to look at their picture that they drew 4 different things all at once there. But, you know, so here's 0, here's 2 pi. This is the theta axis. And then up here, we have u again. And so this is just a normal sine curve when t equals 0. And so that looks something like that. So here's t equals 0. Okay, but now if we let t equal pi over 2, say, well, in that case, cosine of pi over 2 is equal to 0. So then, instead of the boundary looking like I drew it up here with that regular sine curve, it actually, I'll extend that a little bit there too. It actually, so here's 2 pi, here's theta, 0. Now it is simply u equals 0. Okay, because cosine, we've got cosine times the sine, but cosine of pi over 2 is 0. So at that point, everything on the boundary is 0. If we go to t equal pi, then cosine of t is equal to negative 1. And so we get the opposite of this sine curve, opposite in sine, that is, SIGN. So again, 2 pi is theta, 0. And so the boundary would look like this. And if we looked at all these numbers up here, they would just be the negatives of each other. And so on. Okay, so by the time we get to 3 pi over 2, right, t equals 3 pi over 2, This thing's flattened out back to 0 because cosine of t is 0, and so we just get this. Okay, and as we look at this, we can say, you know, again, depending on what these time units are and how long it really is taking to change the boundary conditions. You know, so if this is a very heat conductive piece of metal here of some kind, and we're actually measuring T for some reason in hours or days, then, you know, at any short time, what happens is if we take any 2 points opposite through the origin, then, you know, that if we kept the boundary conditions constant over time, now they could fluctuate around the boundary, but constant over time, then, you know, we would expect on this particular line, you know, whatever this value is, b of theta, and this value is a of theta, then along that line, we would assume that we would see a straight line of temperatures if this could go on long enough at a given set of boundary conditions, you know, boundary temperatures. You know, so maybe they look like this, and then, you know, along, say, that line, we would see a straight line of temperatures starting at -1/2 down here and 1/2 up here, you know, but it would be a straight line if we just looked at that slice. You know, and it would be 0, you know, across here if these were the boundary conditions that we kept in place for long enough. You know, it would kind of get there, but then fluctuate and so forth. But again, you know, most likely these boundary conditions are changing relatively rapidly. And so who knows, you know, what goes on here without actually solving the differential equation. You know, just don't know. And so we can talk about what the boundary conditions look like. And that's what their picture is just on the boundary. But who, you know, we just have no idea what's going on in the middle. So there we go. That is type 1 boundary conditions that they mentioned. And that's where we specify the temperature at the boundary. So I probably should have said way back here to help you out here, type 1. So sorry I didn't do that to begin with, but this is, the video will be named the right way. So type 1. All right, we'll call that done.